Continuing our conversation about data-related operators and directives, which is section 4.3 in your book. The next operator is the type operator. And we've talked a bit about how it's important for when we're doing certain kinds of instructions for the memory size to be the same. So we can easily get the type of something by using the type operator. It returns the size in bytes of a single element of a data declaration. So a byte is 8 bits, so it's going to get a value of 1. A word is 16 bits, it's going to get a value of 2. A D word is 32 bits, it's going to get a value of 4, and a Q word is going to get a value of 8 as 64 bits. Next, the length of operator. It counts the number of elements in a data declaration. So for those of you familiar with higher level languages, it would be similar to length or count in some other languages, essentially giving us the number of elements in an array. So you can see here we have 3 byte elements. We have defined 32 word elements in the second example there, and so forth. So length of is essentially going to tell us the number of elements in a single data declaration. The size of operator combines the first two that we just looked at. It's going to essentially give us multiplication of the type operator and the length of operator. So it's essentially telling us, if we have an array of data, it takes the number of those elements and multiplies it times the size of the element, giving us the total amount of memory used by that particular data. We can have data declarations span multiple lines if the declaration ends in a comma. So you can see in our example here, we have a word array, and it actually has 6 elements to it. 2 of the elements on the top line, you can see the first line ends with a comma. Second line has 2 elements, which also ends with a comma. And then the last line has 2 elements. The length of and size of operators we just talked about will include all 6 elements defined in that data declaration. Next, we have the label directive. And a label essentially allows us to provide an alternate name with a different memory allocation for a variable. It doesn't have any storage of its own, but it really points to, it's a pointer to another label or variable. So in this example, we've got 2 labels. We've got a DW list label, D word, and a word list label. Then we define a byte array with 4 elements. And what we're essentially doing is we're saying, hey, this byte array of int list, we're going to also put that information or reference that information through the word list label and through the DW list label. And so we can access that information from a D word, which is 32-bit, from a word, which is 16-bit, or from the byte array itself. Next, we're going to discuss indirect operands. We've already talked about this a bit with the pointer operator, but an indirect operand holds the address of a variable. And in the context of indirect addressing, we want to reference the value at an address rather than the address itself. So in this case, we have a byte array, val1, that has 3 elements to it. And in our code segment, the first thing we do is we move the offset of that, and that is an indirect reference into the ESI general register. And the offset initially is the first element of the array. Then we are going to move from the ESI register, we're going to dereference that, and instead of moving the number 1, which is the first element of the array, we are moving the actual value at that location, which is the value of the element of that array, which is 10, hexadecimal number 10. We're moving that to AL. Then we increment ESI again, And again, we dereference it using the brackets. And instead of ESI's value, which is 2 for the second element in the array, we are getting the value of that second element, which is 20. And likewise on the last line, the final element of the array. And remember, we use pointer to clarify the size attribute. So here we have a variable, myCount, which is set to the size word, 16-bit, and a value of 0. And we move the offset of that to the ESI register just like before. Now, if we try to increment, it's unclear what the size of that operand is. So in the next line, you can see we use the word pointer to specify that we're incrementing the dereferenced value to 16 bits, and that's okay. Next, we have indexed operands, and this allows us to essentially dereference a register, and I'll add a constant to show an effective address. There's two forms, the label plus the register, and then the label. And you'll notice the form on the right looks very similar to how arrays are referenced in some higher level languages. So you can see the origins of that here. In our example, we have a 3-element word array, and first line of code, we move the number 0 into ESI, and then the next 2 lines are equivalent. We essentially are moving to the AX 16-bit register the value of the offset. So the ESI has the offset, and then we actually dereference it to get the actual value there, which is 1000 in hexadecimal. So this is just another way to do an indirect. This is another example of indirect operands. Now, if you recall, when we are doing offsets, the offset for a byte was 1, for a word was 2, a D word was 4, and a Q word was 8. So rather than having to remember that, we can do something called index scaling, where we essentially use the type operator to multiply times the offset. So the offset can be an indexed value of 0, 1, 2, 3. We multiply it times the type. For a byte, it's 1. For a word, it's 2. For a D word, it's 4, etc., etc. So it just enables us to have code that looks more consistent regardless of the memory allocation for the different labels. Now, we referenced the pointer operator earlier, but we can also declare a pointer variable without explicitly using the operator using this technique. And what we're essentially doing with this is we are pointing, a pointer points not to a value but to the address or the offset of another variable. So in our data segment, you can see we have an array, a word array with 3 elements, and then we define a pointer, and its value is set to the offset or address location of the array. Not to the value, but to the address location. And then in our code, we're moving the value in our pointer, which is the address of the array, into the ESI. And then when we dereference the ESI, it actually, since the ESI stores the address, the dereferenced ESI is going to store the value at that address, which is, at the moment, the value of the first element of our array, which is 1000 in hexadecimal. And then the alternate format of that you can see at the bottom, where we actually explicitly use offset to define the pointer. Next, we're going to talk about jumping and looping. First of all, we have the jump. This is the simpler of the two. It's an unconditional jump to a label, usually in the same procedure. So essentially, the syntax is JMP and then the target. And what it's going to happen is the instruction pointer is going to move to that location in the code. The caveat being we need to make sure that generally we're in the same procedure in order to do the jump. If we want to do a jump to another procedure, we need to use a global label, which we have learned about earlier. A loop is a conditional jump. And this is the beginning of when we are using things in high-level languages, loops, whiles, and so forth. So the loop will essentially use the ECX register, which, if you recall, is what the computer uses as a counter. So essentially, when we use the loop instruction, it's going to decrement our loop counter until it gets to 0, in which case it will stop the loop. Here's an example. We have some code at the top that moves 0 into our AX register. And then you'll remember that ECX is our looping register. So we're actually starting the loop at 5. So we're moving 5 into ECX. Then we have a label, L1, and we are adding the value of CX, which is the lower half of the ECX register, which is 5, to our AX register, which is currently 0. So it'll be, that value will be 5. Then we're going to loop. And when it does the loop, it's going to check the value of ECX, which is 5. It's going to decrement it to 4. Then it's going to go back to the label we specify, which is L1, and run that add again. So it's going to, now the ECX register has a value of 4. And so it's going to add the number 4 to AX. So it's going to be 5 plus 4, and then loop. And it's going to do that until it gets down to 0 and stops. So the value at the end will be 5 plus 4 plus 3 plus 2 plus 1. So copying strings is a pretty common activity in coding, and we're going to use some of the techniques we've just learned to do that. We're going to use the loop and some of the indirect addressing. So you can see we define in our data segment a source and a target. We have defined a source string. Remember, it's byte, and there's a unique format that we use, surrounded by double quotes so that we don't have to do as a comma delimited list. And we have the target, which is going to be the place where our string ends up, using the size of keyword. In our code, we move to the ESI register, value of 0 first, to our index. Then we are going to start our loop counter. We are going to get the size of our source string, which is essentially the number of elements there. And we're going to move that into our loop counter. So then we are going to move our dereferenced ESI value, and we're going to move it to the AL register. Then we're going to move it. Remember, we can't do a move from a memory to memory. We have to move it to a register and then to memory. So we're going to move it to the AL register, and then from the AL register, we're going to move into our target. And the dereferenced is going to take the address location and actually put the value of the first character of our string into our target. Then we're going to increment ESI, which is going to go from 0 to 1. Then we're going to loop. That will move the ECX register down 1. And we'll continue the process. And we will continue to copy one character out of the string until we get to the end of our loop, when we've gone through the size of the original string and our ECX counter gets to 0. As a final note, we got our summary of what we've talked about. We talked about data transfer instructions, move, move SX, move ZX. We talked about different operand types. We talked about arithmetic, increment, decrement, add, subtract, operators, and then finally jumping and looping. So that concludes chapter 4. Thanks a lot.